Hello everyone and welcome to this week's tutorial. First of all, I would like to really thank you for all the great support and the comments and the likes and the messages and everything. I'm really thankful and a bit overwhelmed by how much this channel has grown with just 2 tutorials. So I would like to thank you once again for all the support, and also I would like to announce you that as of this week we are going to have a Patreon where all the project files and other goodies coming soon are going to be available, so make sure to check these. Also, I'm hoping to create a Discord server really soon, so stay tuned for that. And today's tutorial is going to be about Cymatics or Houdini patterns, and it all started with me reading this article on Stash, where I realized that the title sequence for the Amazon's Rings of Power was not CGI as I previously thought, but it was created using an actual Houdini plate and sand and a camera, which makes it even cooler, but also I felt like it was a challenge even more to create something like this digitally. So after doing some research and understanding the math, I managed to create this scene, which is based on the actual math that makes these patterns form in real life, and I've also managed to get my logo in there. So without further ado, let's get started. First of all, let's understand how these patterns are generated. So these patterns appear in real life because a plate is made to oscillate using a speaker and a frequency generator. And why they appear like that is because the areas where the sand sort of settles are area where the plate is not moving or oscillating, so they just settle there. And the math that helps us understand how these patterns appear is described in this great article I found from 2003 written by Paul Borg. And in this article is this equation which we are going to use in order to understand how we are going to make this. After we understand the math behind this equation, we are going to quickly implement it in a new Houdini scene, and after that I'm going to walk you through my actual render scene that you've seen earlier. So let's first of all understand what each of the parameters mean here.
I'm afraid we need to use math.
N and M are just integers which we are going to input in order to control how the patterns are going to look like. Pi is the number pi, 3.14 and so on. X and Y are the coordinates on the X and Y axis. We are going to use X and Z since we are in 3D, and Y is like the height axis. And L is the length of the actual plate that we are going to simulate. And one quick trick, X divided by L is actually what in Houdini we are going to call the relative bounding box. So we are going to use that function in place of this. So what is cosine? Cosine is just an oscillation basically. It's a trigonometric function that is used to describe relationships between like circles, angles, lengths of segments in triangles and stuff like that. But for our purpose today we only need to visualize it, and it looks like this. And what it helps us simulate is an oscillation, and we can control the frequency of that oscillation by messing with how big or small the number is in the parentheses, hence the N and M parameters and how they are affecting this setup. So let's jump into Houdini. Let's create a geometry scene, create a grid. Let's give it a lot of resolution so we have the resolution to work with. Drop down point wrangle. And let's get started with our equation. So first of all, we need N and M. Let's define those. So we have N and M. Now we need x divided by L and y divided by L, which, as I said earlier, is just the relative bounding box. So let's create that. Once again, we are using the x and z instead of x and y because we are in 3D here and y is our height axis. And now let's create the equation. I'm gonna call this time for Cymatics equals to cosine of n multiplied by x multiplied by pi let me copy paste in this, so I'm gonna move faster. Okay, so we have n and x, m and y, and then we have n and x and n and y. So n and x, m and y, and then m and x and n and y. Then we have an error. Oh, it's because I've used z instead of y, my bad. Okay, and now if we plug this into, let's say, the position y, and we add some values to m and n, we can see that our Shalni plate here oscillates. But for our purpose, we don't care if this oscillation is negative or positive. We just want to know how big it is. So let's say that we are going to use the absolute function, which all it does is if there are negative values, they are going to be turned into positive values, and positive values are just going to be left alone. And now you can see the pattern appearing. And how we are going to use this attribute as a force is using a gradient. So let me actually put this into an attribute. Okay, and now I'm gonna create a volume based on this attribute using the volume rasterize. Let's make the voxel scale smaller and the point scale also smaller. Okay, and what we have is this attribute called CIM, which we visualized earlier. Let's also put it into color so it's easier to visualize. We have this attribute as a volume. Now this is a floating point, and what we want is to create from this floating point a force that pushes our particles from these like high frequency oscillations areas that are happening in real life to these areas with low oscillation. And for that we are going to use what is called a gradient. And what a gradient is a vector that's going to point towards the direction where the greatest change is happening, and that is gonna help us to create a force that we can then use to displace particles around. So for that we're going to need a VDB analysis. Okay, let's rename it to vel, and let's actually visualize this force. So let's create a volume trail. And you can see we have now a couple of vectors which all point towards these areas of, actually they point away from these areas of low oscillation. So what we are going to need to do is we are going to need to invert this force, but using -1, let's use -2 here. And now you can see that we inverted these vectors. Let me make the trail length smaller so you can actually see them. Okay. And now with this velocity volume, what we can do is we can create a scatter. A pop network. Let me put a null here so it's easy to find. I'm gonna name this out velocity. And here we are going to need the pop advec by volumes. Let's set it to velocity and point it to our velocity field. And here we want this to invert all points, but only on one frame. Let me hide the source. And now if we simulate this, you can see that our points go to their positions. And this is how you create the Shalny force/velocity field, which I've used in my setup. So now let's jump into the actual Houdini scene, and let me explain you what I did here. So what you've seen earlier is happening here. We have again a grid. We are creating the pattern with the same math that I did earlier. I'm again creating a volume from that, analyzing it. Oh, here I'm also multiplying the velocity in y with 0, because what I've seen in RBD is that I was having some random upwards pointing velocities which I didn't want, so I made this in order to clean that. Here I'm just having like a smaller grid on which I'm having my logo read in by a texture node and multiplied with some noise. I've stashed that because I had some troubles with UVs rotating randomly for some reason, so I just stashed that here in order to make sure that that doesn't happen during the sim. Here I'm just scattering some points using color as a density attribute for the scatter node. Here I'm again creating some noise, but on the original bigger grid that I used to create the volume, and I'm scattering some points here to have some random points around the logo as well. Here I'm adding some more noise to it so the edges are not perfect. Here I'm randomizing the orient attribute in order to have the pieces randomly orient and not have all pointing in the same direction. And here is a little bit of Vex I wrote in order to define p-scale by the distance to the closest point, so there is a very little chance of these objects like intersecting each other, and I'm doing this in order to help I'm doing this in order to help the RBD sim be faster and more stable. I'm also creating a variant attribute which we are going to use to randomize which of the small sort of sandstones we are going to instance on this point. Here again I'm randomizing p-scale here because they are more spread and I'm going to have smaller pieces on them anyway, so there's no risk of collision there. And here I'm also randomizing the variant, so we have randomized pieces on this point. I'm merging them together. Now in order to create the small sort of stones, I'm creating a box, scattering some points on it, and I'm Voronoi-ing it. I'm creating a for each of those small points. I'm centering them down. Then I do a Boolean intersect between the piece and the platonic dodecahedron. And then I'm converting this to a VDB. Here I'm smoothing the VDB based on the current iterations, so that some of the stones are gonna have sharper edges, and some of them are going to have smoother edges and look more like they got polished in time. I'm turning this back to polygons, and because this is really dense, I'm using a remesh with adaptive in order to simplify this for rendering and other purposes. Here is a trick I'm using in order to make sure that these pieces are inside the sphere with the radius of 1. So when I'm using the p-scale attribute with what I created earlier, so that the pieces don't intersect, the sizes are in such fashion that is gonna work. So what I'm doing is I'm bounding my object with a sphere. I'm also having the unit sphere. I'm extracting the transform between the two spheres, and I'm applying it back to the piece that I'm creating. So in this way I'm making sure that the piece is always centered and small enough to fit in the sphere of 1 unit of radius. I'm adding normals. Here I'm creating the variant attribute for the instancing. I'm also creating a new primitive attribute based on the variant, which I'm using in order to randomize the materials. I'm also adding UVs just in case, and then I'm packing these. And now with all that objects and the variant and everything, I'm going inside this copy to points. And as you can see, while there are some intersections here and there, this is overall decently clean, and it also takes care of having some random distribution of size that's more interesting than just some random attribute. Now this goes inside the DOPNet, which I'm not gonna let sim. Here I'm just having the pop-out back by volumes, as you've seen earlier, and I'm also using a pop-out tract in order to push the particles away from the center, which makes for an interesting sort of look and fills the Shalny patterns better. Okay, here I'm just caching that out. And also for like the wider part of the scene, because I felt like these small stones were not enough to fill the patterns and make them be really visible, I added some extra points. Here I'm also creating p-scale by the same principle, because here I'm using pop grains and I need them to have a p-scale that doesn't intersect, otherwise the pop grains is gonna explode. Here I'm also using pop interact to sort of push the particles away even more, so they don't get really crumpled together by the velocity field. The same pop attract to push them away from the center. Now, what I would have done differently right now is I would have probably also created a velocity field from the dop net and link that to the particles, because right now they get, even with the pop interact and the pop grains, they get crumpled together and they are not like in the same exact areas as the RBD, which makes it look a little strange. So this was the setup. Thank you for watching, and I'm looking forward to seeing you next week. Also, I'm looking forward to see you on the Discord server when that gets created. And bye bye.